This is my physics lab 1 of constant velocity by me, Saksham Bhardwaj. Here's some background info. So the way this lab worked out is that I took a video of a cart rolling across a track at roughly constant velocity. There's no force on the cart because the velocity should be constant, and there should not be a change in the direction of the cart. According to Newton's second law, the object should in theory be traveling at the same velocity forever because of the fact that there's no net force. However, that's not exactly true because there are some forces at play that we can't describe, such as air resistance and friction, and that's why we're comparing this cart to a computational model on GlowScript. So here's some key equations. There's a momentum principle equation, which is the net force impulse equals the change in momentum. Position update equation, which shows the change in position based on an average velocity, which should be constant throughout the whole entire experiment. And the velocity update equation. I'll talk more about these equations later in the code. Here are the initial conditions. So the initial position was in the computational model was set by the initial position from the tracker data of the cart that was analyzed in the tracker program. And same thing with the initial velocity. It was taken by the first two timestamps and the distance traveled in those first two timestamps, and the velocity was taken with that delta t of 0.02 seconds. And there's no net force. There we go, tracker time. The video that recorded all the data. Here's the push of the cart right here, going at roughly constant velocity, and as you can see here, the data is being recorded for every delta t, and that is the tracker data. Here is my code for the computational model. The mass of the cart was represented by a ball, which is approximately half a kilogram of mass. Here's the initial position vector from the tracker. Here's the initial velocity vector, also from tracker. Here's when the video in the tracker started, about 3.59 seconds, and it ended after about 6.6 seconds. The net force obviously is 0. Here we're using the velocity update equation, applying the momentum principle because change in momentum equals force times delta t. And the momentum divided by mass is the change in velocity. So you got force divided by mass times delta t, which is just force times delta t, which is the change in momentum, divided by the mass, which is the change in velocity. And this updates the ball's velocity. However, this part of the equation should always equal 0 because there is no net force. Next up, the ball position being the position update equation, as seen in the slideshow as well. And this just advances the clock, and that's all that I changed for the program. Tracker data and the computational model data. Here's just the tracker data. Here's the computational model data. As you can see, the computational model has an r-squared value of 1 because it's literally just a linear equation. Now comparing the two graphs, with yellow being the computational model and blue being the tracker data, it can be seen that at the beginning, the yellow almost completely engulfs the blue line. However, later on, the blue line slows down, whereas the yellow computational model stays constant as it should be. And there are many reasons for this, which we will discuss later on. As you can see, the slopes are pretty different, so of the trend lines of both the data sets. We followed a linear path with a nearly constant velocity, with the r-squared value being very close to 1, which shows that it almost was fit by a linear model. The cart travels slower than expected, as you can see by the differences in slopes of the two trend lines. So there is some error. One big source of error was that the original push of the cart was from a spring. A spring, according to Hooke's law, applies a net force on the object, which is what we did not want. Additionally, the camera angle as the cart got further away, it looked like it was traveling less distance for the same amount of time, so that can mess with the velocity and make it lower than it should be. Also, the track still could have had some friction present. So here's the what if question. So if you were to flip the axis around, that would mean the displacement would be in the negative direction, as seen by these graphs here. So the displacement, as you can see, this is in the x direction. In the negative x direction, it would be the same slope, but in the negative direction, the negative side of the x-axis. And if you look at the velocities, the speed would be the same, and the magnitude of the velocity would be the same. But if it was in the x direction, it would be positive, and the negative x direction, it would be negative. So what does it all mean? So how can you say for certain how many pushes and pulls go into the net force being 0? you can't really say for certain because there's too many forces to keep track of, and there's so much going on. But two forces we know about for sure that cancel each other out are gravity canceled out by the normal force. And that's the end.